Hey guys, welcome back. This is going to be a series on how to do OpenGL programming, specifically on a Raspberry Pi 4. For veteran programmers, this probably wouldn't be very difficult, but I had a bit of a problem, a bit of trouble trying to get this to work on a Pi 4. There's some quirks of the Pi architecture that you should know if you're going to be doing this. So it is important to know that all Pis, save for the Pi 1, can do OpenGL 2.1. They all have the hardware in the video core processor. However, it starts breaking down if you try to do more advanced things. So the Pi 3 and the Pi 4 can do OpenGL 3.0 perfectly. There is all the hardware for it. OpenGL 3.1 is mostly supported. Apparently, if you try to do OpenGL 3.1 development or games, most likely they'll run fine. There may be like a couple of things not quite right. OpenGL 3.2 is where it really starts breaking down. There isn't the correct hardware to do all the 3.2 stuff. For the video core 4 and the video core 6, so they just don't have the hardware for it. So at your own risk, do OpenGL 3.2. Now OpenGL 3.0 is far and away more versatile and one would say more powerful than OpenGL 2.1. ES is for embedded systems. In fact, the Pi Foundation has completely foregone 2.1 development and embraced the OpenGL ES development. So if you ever notice OpenGL updates from the Pi Foundation, those are most likely ES and not OpenGL proper. There will never be OpenGL 3.0 or higher on the Pi 3 or 4, as far as we know, because those hardware functions just simply do not exist. There is Vulkan, but that's a totally different beast. And that is outside the scope of this video. So for this first part, I will show you how to set up your Pi for OpenGL development. I'm using a remote Pi. I'm not going to be developing on it locally. On board the Pi, I'll be developing it somewhere else in the network. I find this easier, faster. You don't have to deal with a slow Pi. Even though Pi 4s are fast, your laptop or desktop is probably going to be faster. So let's go in. Now, this is a PDP-11 emulator, so you probably won't have that. So let's exit out of that. The first thing we need to do is install Mesa Utils. Mesa Utils it has the GL base driver, as well as some tools that we will want, just for debugging purposes. So that's sudo apt install Mesa Utils. I already have it. But this is what you will want. Next, you will want freeglut and libglue. The thing with OpenGL is that OpenGL doesn't actually do anything on your screen. It does things in your video memory. So in order to see things, you have to have a window manager. And this is what glut and glue do. Glut itself is a very old OpenGL library. Remember, OpenGL came back in like the 90s. Glut is very good, but freeglut is a little better. It's more up to date. Glue, I use glue for shaders, which we're going to be doing way down the road. But freeglut and glue are the two things that you will need. There's GLFW, there's SDL, there's a bunch of other window managers. We're going to be doing freeglut and glue. So sudo apt install freeglut 3-dev and libglue, what is it, 2.1 and libglue dev. Okay, I already have them installed, but that's what you need to know. Now we can go see what OpenGL versions are supported. We do this by doing glx info pipe grep OpenGL version. As you can see, I have the Mason 19.3.2 driver. You can build more recent ones if you want to go down that road. But most importantly, this will be doing 2.1. This is a Pi 4. I can do OpenGL 2.1. Now, it is also important to note that if you try this on a Pi 02 or a Pi 3, you might get OpenGL 3.1. This is false. You are not able to do 3.1. 2.1 all the way throughout the stack. If you don't get this message and you get something that says couldn't open display, I will show you how to fix this. What you got to do is you have to put a display variable in your environment. You can do this simply by doing export display equals :0. Or a better way to do this is to do this into the bash rc. Sudo vim bash rc. Go all the way down. As you can see, I already have it. Export display. This really is just, it's which display you have. Usually you only have one display, unless you have multiple VNC sessions. This is the one that you're going to be doing. Okay. And let us prep the Pi for VNC development. So we're going to go into the Pi config. Sudo raspi-config. This is what you want to do. Go to System Options, go to Boot, Auto Login. This was a headless Pi for the longest time, the server, so I just did console auto login. You want to do desktop auto login. So change that. I already changed it, so I'm not going to be doing that. Then go to Display Options, go to Resolution. I just have 1920 by 1080. You change it as you need to. For some reason, or sometimes the default resolution, 720 by 40, just doesn't work well with VNC. So keep that in mind. Then of course you need to turn on VNC. Some of you Pi programmers will remember VNC just being kind of a pain to set up. Luckily it is integrated into the Pi directly. So go to Interface Options and then you just hit VNC and turn it on. And it will work. The Pi will probably ask you to reboot. That's totally fine. Let's go here, VNC. And as you can see, I already have the Pi. Let's load it up. That's right. And here we go. We are in my Pi. And we are ready for OpenGL development. And that will happen in the second part. Okay, so now that we have the setup out of the way, let us start the second part of this video and get something shown up on the screen. So I'm going to be using Visual Studio Code. Just absolutely love it. What we're going to be doing is going to need SSHFS. It is a remote file system development extension. If you need it, it's just literally SSHFS. This one right here. And it's pretty awesome. Basically, this is all you got to do. You got to, and let us add a new configuration. Well, seems I totally messed up the label, but whatever. Add to workspace. Where is desktop? Let us add a folder. Let's say GL2. There it is right here. New file. Let's say gltest.cpp. We go in here. Here it is. And here, yes, I do want to install extensions. Cool. And let us start programming. So of course, we gotta do the headers. Code stream twice just in case some things need malloc or whatever. And then include gl glue.h include gl freeglut.h. argc jar argv. Let's change that. And I keep programming in C, so you know how it is. Now that we are ready, let us SSH into this Pi. There we go. Desktop, GL2 touch. Let's make a build file. Chmod plus x build.sh. And okay, okay, let us make this build script. G++, what is it, gl test.cpp, ogl test, w all. Now let's link OpenGL. User include lgl lglue lglue lglut. Save it. And start building it. There we go, it is built. Now let us write some code. So the first thing you got to do is you have to initialize glue. Init and argv. Then we want to initialize the display mode. The display mode, you can do single, double, or triple buffering. You might be able to do quad buffering, I'm not quite sure. Just do double for now. It'll save you a headache later. Single's fine, but double is pretty standard. And also initialize it with RGBA, so you will have an alpha channel for transparency and blending. So let's do that. Glut init display mode glut double and glut RGBA. Okay. And then now we got to set the window stuff. We're going to be doing a window, so let's do glut init window size. Let's just do 500 by 500. Then also there's a little trick you can do. You can do init window position, so it just won't open randomly somewhere on the screen. So you glut init window position 100 100. Okay. Then let us create the new window. So glut create window. Remember, this is a glut tutorial. This is a free glut tutorial. There's other window managers, and each one has different quirks. Let's just call it square. And now you need to point glut to the display function you want to use. There's going to be a bunch of functions you need to point glut to, but for right now, for this tutorial, First video, we're just going to do one, the display function. Glut display func, and just put in a pointer to the display function we're going to be using. And of course, you need to add that up here. Void display void. There you go. There's the display function. And of course, you need to run the loop. You need to run the glut loop. Glut main loop. Okay, so what will happen is the glut will initialize with all this code, and then on every loop, it will run the display function. Every single frame, it'll run display. Before we go any further, let's try building it again. Did I say glue in it? Did I say glue in it? I meant to say glut in it. Let's try that again. There you go, it is built. And now if you run it, you can see that there is a window here. It doesn't look like much, and it looks kind of buggy, but don't worry, it's not actually buggy. We just don't have anything put in the display. This literally grabs screen memory, and that's what it is. So I guess we have to fix it. Okay, so first of all, let's clear that window. GL clear color, and color, because we do RGBA, it's red, green, blue, alpha. So let's just do black, right? 0.0F, these take floats. 2, 3, 4. Alpha works, for veteran programmers, you know how this works, but alpha works also from 0 to 1, 1 being completely opaque, 0 being completely transparent. So we don't want any transparent blending. There's no point, so we're going to be doing 1 for alpha. But if you noticed, when we ran it, it's not black. Why is that? Well, that's because we didn't actually swap buffers. See, we were doing double buffering. You have your screen memory, which is what you see, and then you have the virtual memory of what you're building. So you're going to be building a frame, and then when you run GL swap buffer, it's going to swap what is on the screen and what you have in your virtual memory. It's going to swap them. And so that's how you draw to the screen. So we have black. We had the black color, but we don't have it pushed to screen memory. So let's do that. Let's do GL, glut swap buffers. And then right here, rebuild it. GL test. Look at that, we now have a black screen. And we should do swap buffers just once for every display, because it's efficient, and that's just how you're kind of supposed to use it. Of course, there is no law saying you can't do swap buffers multiple times, but this is how you're supposed to use it. And it's more efficient that way, especially on a Pi where, remember, this is GL, so it's a CPU call to the GPU to do something. So every time you have a line of code that isn't specifically shader code or something like that, it is the CPU talking to the GPU, which slows things way down. So now in here, let's do some code. While we're at it, GL clear, let's clear the buffer bit. GL color buffer bit. Gotta be honest, not quite sure what this does. You're supposed to have it kind of outside the scope of the video about why, but there you go. Now let's do something extremely important. GL load identity. What this does is it resets, simple answer, it resets your view. Now let's get into the nitty-gritty of OpenGL. OpenGL works by taking you, the user, called the origin, and placing that origin at 0, 0, 0 in a three-dimensional space, three-dimensional Cartesian grid. The problem is that you have a flat computer screen. And the way this works is it takes your three-dimensional projection of what you have drawn and projects it onto your screen, onto a two-dimensional surface, which is why you will see warping. This is why if you played games, the objects on the sides look totally distorted. That's just because that's the nature of the beast. It will be distorted. And in order for all this drawing to happen, you have to take the entire three-dimensional world you're in, rotate it and translate it around you, the origin. Draw, retexture, do all that stuff. And then do an identity multiplication on that matrix to reset the entire view back to origin, back to you. So load identity is essentially loading the identity matrix of the world you are in. We will talk more about this later on in this series. Just know for now that GL load identity just resets your view. So GL load identity is also one of those functions you're supposed to run only once. Many people, especially on Stack Overflow, will say you're supposed to use GL load identity only once in your code. But don't listen to them. It really helps, especially when you're trying to draw a bunch of objects and you start losing track of where you are in space. It really helps. It does cut into performance a bit, but it is what it is. Now, let us actually draw something on the screen. In GL 2.1, you can do points, triangles, quads, I think polygons, but that's all those kinds are sort of outside the scope. Let's just draw a square. Too many people are drawing triangles. Let's just draw a square. So we start this by doing GL begin. Okay. And then you finish it by saying GL end. Do note this is a OpenGL 2.1 specific thing. OpenGL 3.0 and onward have deprecated begin and end. Now you have to tell begin what kind of drawing mode you want to be in. Let's do GL quads because we want to draw a quadrilateral. And let's do it. GL vertex 3F. We're going to have 3 floats, right? Vertex. And let's just draw a square. Negative 0.5, negative 0.5, 0.0F. And you may be wondering, why is this 0.5? Why isn't it some other arbitrary number? Well, this is another thing of OpenGL. OpenGL works on your window space as -1 to 1 and -1 to 1, or -1 to 1. You are 0, 0. The center of the screen is always 0, 0. That's where you always are. -1, 1, -1, 1. Doesn't matter how big your objects are in the world, doesn't matter how far away or how close, it's always -1 to 1. So when I draw a square, -0.5 to 0.5, that's going to be half. That's the top of the square will be half up, the bottom of the square will be half down, so we'll be able to see it. If we did 1, 1, 1, 1, right, then the entire window would be filled with the square, and it would look white. You wouldn't see the square. You would see the square, but it would take up the entire window. So we're cutting it in half. Quarters, technically, right? And we need 4 points, 2, 3, 4. And then let's just do the quick and dirty way of drawing a square. There we go. And we now have, basically we have the 4 vertices for a quadrilateral and end to tell OpenGL to stop drawing, stop sending draw command to the GPU. And then you swap buffers. Let's try building it. Well, let us take a look. Why does this look the way it does? Ah, yes. This should actually be negative down here. Let's try that again. Look at that. There we go. Now it's fixed. It is now a square, and actually I should probably put F's here. It's probably fine, but for posterity's sake. And build GL test. There you go. We now have a square being drawn on the GPU of a Raspberry Pi 4 in OpenGL 2.1. And before we go, actually, let's add something to the build script. Check this out. We can have the build script run the program on a successful compile. So check this out. If we do if, what is it? $? Right, $? is the return code. I think it's register, I want to say register 8 contains the return code on ARM processors. If GCC or G++ returns a 0, that means it was a successful compile. Then start it, GL test, and then end the if. Let's try building it. It was a successful compile, and it runs automatically for us. And if we misspell something, put that back to C, it doesn't run because there was an error in the code. So we can go back, fix it, and try again. There you go. This is set up, ready for your use. Next video, we will cover resizing the window, which doesn't have too much bearing on anything quite yet, but it will in the future. A lot of OpenGL programming, or many big library programming, is setting up the boilerplate first, and the fun stuff happens later. And unfortunately, that is the case for this, which, in my opinion, which is why the learning curve is so steep. You don't see results very quickly in OpenGL. But I'm here to help you move as fast as you can with programming OpenGL 2.1 on the Raspberry Pi. Thanks.